if a cyclist travelling with linear motion accelerates uniformly from 5 to 7 meters per second in 10 seconds, and then continues to travel with constant velocity for another 10 seconds, before decelerating right down to zero at a rate of 0.5 meters per second squared, then how far has he travelled in total? There are actually a couple of ways that we could go about solving this problem, but the first thing that I wanted to point out is that a straight line on a velocity-time graph represents constant acceleration. And so although the acceleration of the cyclist is not the same throughout, we could divide the graph into 3 intervals where the acceleration in each interval is constant, and what we could do is we could use the SUVAT equations to find the total distance travelled in each interval, and then take the sum of those distances to see how far he's travelled in total. However, since we know that displacement is the integral of velocity, then what we could do instead is we could find the area below this graph, so the integral of this velocity-time graph, and that would represent how far he's travelled in total. But in order to calculate the area below this graph, we're going to need to find the value of t when he reaches a velocity of 0. Now remember, after 20 seconds, he begins to decelerate at a rate of minus 0.5 meters per second squared. And because acceleration is the derivative of velocity, that means that the gradient of the velocity time graph after 20 seconds, so this straight line here, the gradient of that line is minus 0.5. So minus 0.5 is equal to the change in y over change in x. So this delta sign right here means change in, so change in y over change in x. The change in y is from 7 to 0, so the change in y is minus 7, and the change in x is what we're trying to find. So let's just call it capital T. Now if we rearrange this for t, we get t is equal to minus 7 over minus 0.5. So capital T is equal to 14 seconds, so the cyclist comes to rest after 34 seconds. So now we've got all the information we need to be able to determine the area below the graph. So if I draw a dotted line like this, and another one over here, and one last dotted line across here, then we've divided the area into simpler shapes that we know how to find their area. So the area of this rectangle is 5 by 10, so we have an area of 50 here. And for the triangles, we know that the area is given by a half base times height. So the height is 2, the base is 10. So the area is a half times 2 times 10, which is 10. The area of this rectangle here is 10 by 7. So we have 70 for this rectangle, and then again half base times height, we have 7 by 14. So the area is 7 times 14 times a half. So 7 by 7 is 49. So the total area here, the sum of these areas, represents how far the cyclist has travelled in those 34 seconds. So if we take the sum, we have 10 plus 50, 60 plus 70 is 130, plus 49 is 179 meters in total. For our next problem, we have a train again travelling with linear motion between 2 points A and B. The train passes point A with a velocity of 54 kilometers per hour and then begins to decelerate at a rate of 1 meter per second squared, and then 10 seconds later the train passes point B. So let's try to find firstly the speed at which the train passes point B, and secondly the distance between the 2 points. So we've been given the initial speed, we've been given an acceleration, and we've been given the time it takes for the train to travel from A to B. And because acceleration is constant, or I suppose I should say deceleration is constant in this case, that allows us to apply the SUVAT equations to solve this problem. So let's start off by converting 54 kilometers per hour into meters per second. So the initial speed u is equal to 54 kilometers per hour, which is equal to 54,000 meters per hour, because there are 1,000 meters in a kilometer. And in order to convert from meters per hour to meters per second, we're going to divide by the number of seconds that are in an hour. So there are 60 seconds in a minute, 60 minutes in an hour. So we're dividing by 60 times 60. And this comes out as 15 meters per second. So our initial speed is 15 meters per second. So let me quickly get rid of this. Acceleration is -1 because we're decelerating, and t is 10. So we've been given 3 of the SUVAT variables. U is 15, t is 10, and a is -1. And let's start by finding the velocity of the train as he passes B. So this is what we're trying to find. And at the moment we're not interested in finding S. And when you want to choose the equation that you want to use, pick the equation that doesn't involve the letter that you're not interested in. So we're looking for the equation that doesn't involve S. So that's the top one. V equals U plus AT. So V, what we're trying to find, is equal to 15 plus -1 times 10. So V is 15 minus 10. V is 5 meters per second. But if we wanted to convert from meters per second back into kilometers per hour, then we'll do the opposite conversion of what we did earlier. So now we're going to multiply by 60 squared, and we're going to divide by 1,000. And this simplifies to 18 kilometers per hour. So we've got the speed at which the train passes B. Let's now try to find the distance between the 2 points A and B. Okay, so again we know that t is 10, we know that a is -1, and we know that u is 15 meters per second. And although we do know what v is, we can write across below anyway because we only need three of the letters. So s is what we're trying to find. So let's use the equation that doesn't involve v. So that's s equals ut plus a half at squared. So s is equal to 15 times 10 plus a half times a is -1, t is 10. So a half times -1 times 100. So s is equal to 150 minus 50. So the distance between A and B is 100 meters. For our last example, we have a particle being projected vertically upwards with a velocity of 12.5 meters per second, taking up to be the positive direction, and the force of gravity is going to cause the particle to accelerate towards the ground at 9.8 meters per second squared. And we have to find the maximum height reached by the particle. So let's start by jotting down what we know. So again, if we take up to be our positive direction, then the initial speed or the initial velocity is 12.5 meters per second. The acceleration is being directed towards the ground, so we have negative g as the acceleration, and we also know that the particle is going to have a final velocity of 0, because when a particle is at its maximum height, then it's going to be instantaneously at rest. So we know A, we know V, and we know U. So let's write that below each letter. So V is 0, A is negative g, and U is 12.5. We're trying to find the displacement above the ground. So let's put a question mark below S. And we're not interested in finding t. So the equation that we're going to use is going to be the equation that doesn't involve t. So we're going to be using the last equation, v squared equals u squared plus 2as. So v is 0, so 0 is equal to 12.5 squared minus 2g times s. So if we rearrange this, we get s is equal to 12.5 squared divided by 2g, or 2 times 9.8. and this comes out as 8.0 meters to 2 sig fig. Hey guys, thanks so much for watching. I hope you found the video useful, and if you have any comments or questions, post them down below and I'll see you next time.